Yes, if you have any question, just let me know. Okay, so we were discussing about how to calculate, how to know the order of reaction and okay, how to know the order of reaction and how to calculate rate constant. As I discussed last time that it is difficult to measure concentration at a given time in a lab, and so what people do is they measure a physical property which is proportional to uh, concentration. A good thing about this is you don't need to measure uh, your physical property of reactant. You can measure total physical property. And if you can measure total physical property, then there is a relation which exists between uh, this ratio ln a by a x particularly, uh, which is equal to P infinity minus P0, P infinity minus Pt. So here we have used pressure, but any physical property can be used which is proportional to concentration. I discussed one example uh, that is about dissociation of ammonia to nitrogen and hydrogen gas. We showed you that I showed you that like A is proportional, P naught is proportional to A, then your PT is proportional to this quantity, uh, which means PT is proportional to A plus X, and P infinity proportional to 2A. On that basis, we calculated that P infinity minus P naught is proportional to A, P infinity minus PT is proportional to A by A minus X, and so A by A minus X is equal to this thing. Okay, A by A minus X is equal to P infinity minus P naught by P infinity minus PT. This is for one reaction. But then I discussed this case, which is A to P. In that, I showed you that it is, if I measure, suppose A is gas, P is gas, then P naught is proportional to A, PT is also proportional to A, and P infinity also proportional to A. In that case, pressure cannot be used to know the rate constant or to see that whether this is a first order reaction or second order reaction. In that case, you have to measure a property which is in which proportionality constant, although it is proportional to concentration, but proportionality constant is different for different species. And one example I told you is conductivity measurement. So conductivity of 1 mole of different reactants or different product will be different. It means proportionality constant is different. I showed you by example this y naught, which is any physical property at time 0, is K1A. Yt is given by this equation, and y infinity is K2 into A. And then again, same kind of equation you can get. Only thing is that here physical property which Chujen was different. Okay, Chujen was different. So that's what I discussed. Here I showed you by calculation that physical property where proportionality different for A and B. That is for A it is Ka and for B it is Kb. Using that you can derive this equation. Okay, so these are the two different cases. Then third different cases, just to show that this equation is valid for any reactions which you can think of. I just choose one A plus 3B going to 2C plus D. Okay, so at time t is equal to 0, let's assume that A mole of A has been taken and B mole of big B, reactant B is chosen. And this is 0 amount, this is 0 amount. So in that case, T infinity will at T is equal to infinity, it will be 0. This will be B minus 3A. So A is basically reactant, A is limiting reagent. And so all of A can be utilized, not of B. So B minus 3A, this will be 2A and A. And then you can do same kind of calculation and you can see here that Yt is given by K1 into A minus X, K2 into B minus 3X plus K3 into 2X plus K4 into X. All right. So for every reactant, this rate constant is different. Okay. So just please keep that thing in mind. In that case, again, I calculated Yt minus Y infinity will be equal to minus A minus X plus this constant. Y0 minus Y infinity is minus A plus this constant. And you can see both these are same. So if I calculate Yt minus Y infinity by Y0 minus Y infinity, I will get A minus X by A. So this ratio can be calculated. So please keep in mind that this ratio will can be calculated using this equation Yt minus Y infinity by Y0 minus Y infinity. Now you can also write Y infinity minus Yt by Y infinity minus Y0. It doesn't matter because, okay. Okay, so once you know that, if you have any question here, just let me know. No questions? Okay, then I will go ahead. Am I audible?
Yes, sir.
Okay. Okay. So let's go and discuss about for first order reaction. We already saw that I can calculate A by A minus X by using this equation. So I can simply write log A naught by A is equal to ln Y naught minus Y infinity divided by Yt minus Y infinity. You can also write different way Y infinity minus Y naught by Y infinity minus Yt. And now it is quite easy to calculate. Remember that I have to measure any physical constant which is proportional to concentration. Now I am not limited to know the concentration of reactant only. Okay, I can measure the physical property of entire solution, and that is the beauty of this equation. Okay, for example, if you are dealing with uh, you know a reaction in which reactant and products are optically active, you can measure optical rotation. Okay, optical rotation. You can measure optical rotation. You can measure viscosity also. You can measure volume. You can measure pressure. So anything which is proportional to, you can measure conductivity. So anything which is proportional to concentration can be measured. And now we are not limited to measure your concentration of reactant only, or physical property of reactant only, which is a bit difficult. Okay, it is very difficult to measure in a mixture concentration of a particular species. Okay. Okay, so this is for first order. What about second order? What we can do? Now remember this, that this equation is valid irrespective of what is the order of reaction. If you remember here, I didn't consider anything that it is a first order reaction. Just by stoichiometry, we are able to prove that A by A minus X is equal to P infinity minus P0 by P infinity minus Pt. It is just that we applied this to first order reaction. But till now, at this point, till this point, I didn't consider that it is a first order reaction. So A by A minus X is going to be equal to P infinity minus P0 by P infinity minus Pt. Okay, and that's what we are also going to use to know the second order reaction. So, if suppose if I plot ln yt minus y infinity versus t, then I should get a straight line which tells you that the order of reaction is first. Okay, it is a first order reaction. But if suppose it is not a straight line, then certainly I am not going to use this equation. Then I have to look at what I can do for second order. Second order, just look at whether it is second order or not. You can try zero order also. So let's go and think about, if it is second order, what kind of equation we can use. Okay. So this is for the second order reaction. Am I right? This equation we have already derived, that 1 by A, where A is concentration of reactant A at any time. Okay, at a given time, minus 1 by A naught, which is here, this is your initial concentration of A, is equal to K into T. Am I right? Now what we will do, we will manipulate this equation a bit. Okay, please mute yourself. Someone has not muted. Okay, so let us see this. So what I did in the second step is multiply numerator and denominator by A naught. Okay, what I will get is A naught by A minus A naught by A naught, that is 1, is equal to KT A naught. Now look, why I did that? Because now I have this ratio, A naught by A, which is basically A by A minus X. And we know what is A by A minus X. So this minus 1 is equal to KT A naught. In that case, I need to know initial concentration of reactant, which is very easy to measure. Right? Which is very easy to measure in the solution. You can always, whenever you work in a lab, if you are, you start a reaction, then you have to weigh your dissolving solution, and then you can calculate molarity of that reactant. So it is easy to calculate. What is not easy to calculate is concentration at given time. All right. And then again, there is a problem that concentration at given time, probably you can, because there are different species, so it is very difficult to measure concentration of a particular species at a given time. Am I right? So if I have this equation, I can simply write A naught by A is equal to KT A naught plus 1. And I know how to measure this. This is nothing but Y naught minus Y infinity by YT minus Y infinity. Or you can, again, I can write Y infinity minus Y naught by Y infinity minus YT. Okay. So this is the actual integrated rate law which we use, because it is difficult to measure concentration at a given time. Okay, so this is integrated rate law, and now I can know whether the reaction is of order 2 or not with respect to certainly A. If we can know that, we can, if it is a straight line, then we also can calculate rate constant of that reaction. Rate constant of that reaction. Is there any question? Okay, so after tomorrow's lecture, I will also provide one tutorial. So please go through that and try to solve it. It will give some question for you to work at home. Okay?
So,
Yeah.
in this, which graph are we plotting to determine the order?
Tell me you what graph you can plot. What generally we plot?
The concentration versus time.
Yes. So we can also do like this. Yt minus y infinity by or y0 by y infinity, yt minus y infinity versus t. Am I right? Or you can simply plot 1 by yt minus y infinity. Then this will be a constant. This will certainly be a constant. So there are two ways in which you can plot. One is simply take this ratio and plot versus t. You will get a straight line. Am I right? 1 plus. So with time this will increase. For example, this way. And this will be equal to 1. This will be equal to 1. Am I right? Is equal to 1. And the slope will be equal to, tell me what will be the slope equal to?
K.
K into A naught.
A.
We are plotting versus T, right? We know A naught, so we can calculate the rate constant. Is it okay?
Yes, sir.
Okay. And you can also plot 1 by yt minus y infinity, but in that case, this intercept will be 1 by y naught minus y infinity. And then slope will be k a naught by y naught minus y infinity. So any way you can choose. Okay, so till now we discussed about if there is one reactant involved. Okay, if now we will discuss if there is more than one reactant, then what we do. Okay, so that's what I have written here. That what now we are going to discuss, that determination of rate law for a reaction involving more than one reactant. Okay. In that case, what we do, we do some manipulation. Yeah. The methods which we use is isolation method. Second method which we can use is method of initial rate. So what is isolation method? In which, in this, you have to add large excess of a particular reactant. So I will discuss in the next one. Isolation method. Suppose reaction involved two reactant A and B, then this is the rate law, and that's what we are going to know. What is the value of alpha and what is the value of beta? Okay. So for that, we need to determine the order of reaction with respect to A, and we'll take B in large excess. If suppose I want to know the order of reaction with respect to A, then what we need to do is we take B in large excess. In that case, what happens that B almost remains as B naught because very small amount of B naught is being used for a reaction, since B is in large excess. Am I right? So B is equivalent to B naught, and B naught, since this is not changing, so it is a constant. In that case, V is equal to Ka alpha B naught power beta. Am I right? And since this is constant now, so we can write K into B naught power B beta is equal to K dash. So now rate of reaction is almost same as rate law for a reaction involving one reactant. Then I can apply integrated rate law, for example, and I can get the value of alpha. Okay, I can get the value of alpha.
Sir, a doubt. Like
Yes.
in real life experimentation, when you do this, is the error which you get in this approximation huge, or how do you manage that?
No, no.
Like,
So
what is the
example,
really
so let's think about this. Error A plus B. Am I right? Reaction one is stoichiometry. They are reacting. Okay. So suppose I take 16 times this and one time this. Okay. So if suppose it is like 1 minus 0.5. So what will this be? Now you see, if you look at this thing, it is quite smaller if I suppose take 1 and 1. Then I can certainly not neglect this. Am I right? Because it will be half.
yes?
But here it is easier to neglect it. 16 minus 0.5 is 15.5. If you take suppose 100 times, then error will be even very small, right? Because you are just subtracting 100 minus 0.5. And that when
Yes,
I
so
am
that's what I was
considering
asking.
half of the reaction is complete. Yeah, please go ahead.
कि आप कितना ज्यादा ए लोगे, मतलब वो लिमिट कहाँ तक पहुंचती है, मतलब does that always change with the amount of accuracy you want? So
So
अगर वो
yeah,
बहुत ज्यादा
so again, there are a lot of different things which you need to keep in mind. For example, how much A is soluble in your solvent? Am I right? You cannot go quite high. But if it is soluble, then certainly you can go 100 times, suppose. Okay. So if you go
okay.
100 times, I means mostly you will see there is almost no error. Okay. So you have to keep those things in mind, but sometimes going to 100 time, may not be easy. Okay.
हाँ सर, फिर एक्सपेरिमेंटली पॉसिबल भी नहीं होता होगा, मतलब like if you take, because I mean you should have that much amount in the lab also. Like I was thinking in those terms also. Like, will you have so much amount of, or
ये कहाँ
maybe
पे
if
ये आवाज आ रहा है? साक्षी तुम्हारे इससे आ रहा है?
yes sir, I think अभी मेरे वाले से
Okay. Okay. So yes. So always it will. You see, if suppose you cannot go very high, means I think that 100 time is good enough. But if suppose you cannot go that much high, then probably you have to go by a different way, and that second way. That's why people do second method, utilize second method. So general rule is that first people try method of isolation, or you sometimes it is also known as flooding. So one reactant is flooded and the order with respect to second is calculated. ठीक है, एक का आप फ्लड कर दो पूरी तरह. फ्लड means try 100 times, if not 50 times, something like that. Then you are going to get almost accurate result. But if suppose it is not possible experimentally because of the solubility issue or because of any other thing, or maybe your reactant is quite costly, then you can also try method of initial RA.
Sir, we can decrease the value of B also, concentration of B.
Yeah, certainly
Okay.
that you can do. You are right. Means here we are talking about means you should, only thing that you should get just 1 minute. I will just tell someone to. Sorry, I have to go out because there are a lot of noise. Any question? Yeah. Just please let me know. Is this okay now? Is it clear?
Yes, sir.
Yes, sir.
Okay, so yeah, please. Anyone has other question? No? Okay. So let's go the second way what we can do. That is known as methods of initial rate. Okay, so suppose a reaction involved two reactants A and B, then rate of reaction is given by this. So in this, what we do is that we calculate rate at initial period when time is almost zero. Okay, almost zero. Idea is that A has not been used too much. So A is almost equal to A naught and B is almost equal to B naught because you are measuring rate at the initial times. Okay. So V is equal to given by A naught alpha, B naught beta. And now since I know what is the A alpha, it is quite easy to calculate alpha with respect to A. For example, what I will do is I will change the concentration of A naught. For one reaction where the concentration was A naught, we have already measured rate of reaction during initial time, and at that time I can write this. Now I will what I will do, I will change the concentration of this. I will start the next reaction with different concentration of A naught, keeping concentration of B same. In that case, what I will get is this equation. So you can see that I have not changed the concentration of B. What I have changed is concentration of A, which is now A naught dash. Now I have rate of reaction for both the reactions which started with the different concentration of A. So V dash by V is A naught dash by A naught power alpha. This things cancels out because concentration of B was not changed. And from that I can get the value of alpha. Am I right? Value of alpha. Similarly, we will do in a different way. What we will do that we will take we will measure the rate of reaction for different concentration of B, keeping A constant. Keeping A constant, in that case, I can get the value of B, beta, value of beta. So I can know alpha and beta. Okay, alpha and beta. Please keep this thing in mind that you need to measure rate of reaction during initial times. During initial time, that is very important. So since this is the condition, so this method is quite useful when you are dealing with slow reactions. Okay, it is certainly not good when reaction is very fast. So please keep this thing in mind. For example, a reaction happens in suppose 5 days. Okay, completes in 5 days. So if I am measuring the rate of reaction during first hour, then A is almost equal to A naught. B is almost equal to B naught. Okay, so this is very important. Once you know that this is a slow reaction, then you can certainly use this method. It is quite easy to do that in the lab. You need to keep in mind that only thing you need to keep in mind is that reactions should be slow enough so that you can measure rate of reaction during initial period. Okay, and during that initial period means the fraction of A naught which goes to product should be very small. Okay, any question here? No? Okay. So If the reaction is of first order with respect to A, then you keep, then you will get this equation. If you keep B constant, and if the reaction is of second order with respect to A, then you will get A squared. Here you have 1, simply 1, because reaction is first order with respect to A. Okay. So if you have any questions, just let me know. Otherwise, I will go ahead. Anyone? No questions? Okay, great. So now, second thing which I am going to discuss is suppose reaction is very slow. Am I right? If reaction is very slow, what I should do? In that case, it is difficult to measure any physical property at the completion of reaction. Right? Means Y infinity or P infinity, it is, you cannot measure. Suppose a reaction happens in 5 years. You will not wait till 5 years to know what is the value of Y infinity or P infinity. In that case, what we should do? So that I am going to discuss. Okay. So the method which we generally use is known as Guggenheim method. Okay. And what I am going to discuss with the first order reaction. We have already calculated this, that log Pt minus P infinity by P naught minus P infinity is equal to minus Kt. Okay. If P0 minus P infinity is up, then it will be plus Kt. It doesn't matter. Please keep this thing in mind. Okay. Now P infinity, it is difficult to measure. In that case, what I should do? How we can go ahead and know if the order of reaction is 1 or not, and how I can calculate the value of K. Okay. So now just what you need to do, you have to manipulate this reaction, this equation a bit. That's what I have done here. Pt minus P infinity by P0 minus P infinity. So log, if you take this side, you will get exponential minus Kt. And now Pt minus P infinity is equal to Pt minus P infinity is equal to P0 minus P infinity multiplied by exponential minus Kt. Am I right? And then what we can write is Pt is equal to P infinity I have taken to this side. So Pt is equal to P naught minus P infinity exponential minus Kt plus P infinity. All right, this is the equation. I have simply simplified what we got, what we have already discussed. So this is whole equation. Now what he proposed, Guggenheim proposed that you measure the physical property, so there are two measurements. One is, suppose I am doing at 10 minute first measurement, so 10 minutes. Then what I should do, I should also measure 10 plus 5 minutes. That is 15. Either 5 is tau. Suppose the second data which I measure is at 60 minutes. Okay. Then I should again 60 plus 5, 65 minutes. So pair of measurement should be done with the same interval between these two, between a pair of measurement, the time interval should be same. So should be fixed, and that what is known as tau. So 5 is tau is 5. So if I'm measuring, rate of reaction, measuring a physical property at 10 minutes, then I will also measure at 15. I am measuring at 60, then I will measure at 65 also. If I am measuring at 180, then I will again measure at 185. So measurements should be done in pair. Okay. If I do that, then I have another equation. T will change, but tau will remain same. So now what I am saying that, if I have measured a physical property at time t, I will also measure physical property at time t plus tau. In that case, what I will write is t plus tau here. That's all. Nothing will change. Now time is t plus tau. Am I right? Now what we do that we subtract these two equations. This is first and this is second. And then what you do? First minus second. Okay. So pt minus pt plus tau. P0 minus P infinity is common, so you can take it as a common. Then what you got is exponential minus kt is also common. If you can look at exponential minus kt also comes out from this. Exponential minus kt also comes out from this. So this is common. P infinity cancels out. So what you are left with from this, you will get the factor of 1. And from this, you will get exponential minus k tau. This thing you will get. Right. Now, just take log of that. What you can write is ln pt minus pt plus tau is equal to this whole quantity plus this and minus kt. Exponential minus kt, log of this is minus kt. Now, if I plot this versus t, you see, now here there is no infinity term. Okay. So what I need to measure simply ln pt minus pt plus tau versus t. I don't care about this. This will be intercept. What I will get is slope as rate constant. Slope equal to rate constant. So intercept has this term p infinity, but I don't need to measure. What I need to simply measure physical property at time t and physical property at time t plus tau. If I can measure that and then I plot versus t, I will get a slope which will be equal to k, and that's what we are interested in. I'm not interested in this intercept. What I am interested is slope. And if I plot this pt minus pt plus tau versus t, it should be a straight line. Because you see, these all are constant. P0 is constant, P infinity is constant, tau is constant. These all are constant. This is not going to change. So this versus t should be a straight line for first order. I have started with the first order. So it should be first order reaction if I get a straight line. And slope will give the value of rate constant. Okay? If any question, just please let me know.
Sir,
This is very important. Yeah.
so what should be the ratio of tau and t?
Tau and t.
Like what is the range which is acceptable? Like where the equation will work?
This equation will work whatever the value of tau is. But generally, you should prefer that it should be 5 to 10 minutes, which you can easily do. If you think that 10 minutes is not good enough, you take at 15 minutes. Okay?
And sir,
this is very slow reaction. You remember that. Things will not change that much. So 15, even half an hour. But every measurement, if you think that half an hour I am going to measure, then you take after half an hour. Okay, so certainly you are going to measure in like 2 hour, 5 hour, something like that. Am I right? So in that case, half an hour you can give the time tau interval of tau. Yes, please go ahead. Another question. Yes.
Sir, if we take the value of t to be 10, then also can tau be 10?
Yeah. It doesn't matter. 10, 20, it doesn't matter. If you are taking first value at 10 minutes, then only thing you need to make sure that every time you are taking after 10 minutes. Okay.
Okay, sir.
Okay. Any other question? No. So this is one of the. Remember, this generally we use when we are dealing with a slow reaction. Okay. Good thing about that, if we use this, we don't need to measure P infinity. There is another method, and basically it goes same way. Only thing what we do is in this what we did, we took PT and this equation. But if I write PT minus P infinity, what I will get? This equation. That's what I am going to use in the next one. So PT minus P infinity. Okay, so you will get this equation. P infinity I have taken from this side, I put this side. Similarly, we can do PT plus in tau minus P infinity, I will get this equation. This I have already discussed. Only thing I am doing is taking P infinity from this side and putting, to left hand side. Similarly, P infinity from this side, putting this. And now I am not going to subtract. What I am going to do is I am going to divide this. So Pt minus P infinity by Pt plus tau minus P infinity, and you can see here P0 minus P infinity will cancel out. Then exponential minus kt, exponential minus kt plus k tau. So if I am dividing by this, then this will simply come. Is this okay or something wrong?
So it should be K tau, right?
K tau, you are right? Yeah, it should be K tau. Yes, this will be exponential K tau. Please correct this. This will be K tau. Okay, so what I can write, Pt minus P infinity is equal to Pt plus tau minus P infinity K tau. Okay, K tau. Please correct this. So Pt is equal to 1 minus. So if I take this side P infinity, what I can write is Pt is equal to P infinity plus, okay, and then plus or P infinity plus Pt plus tau exponential K tau, okay, and plus minus P infinity exponential K tau. Is this okay? And now these two term has been written like this. P infinity, if you take common, then you will get 1 minus a exponential k tau. Am I right? Tau or t? Kt cancels out. So nothing, t term is not left out. K tau. K tau. Now tell me what I should plot in this. Yeah? Can you tell me what needs to be plotted? Simply PT versus PT
PT
versus
plus tau.
PT plus tau. You see, this tau is again constant. This everything, this is a constant term, and this is also a constant term. So what will be slope? Slope will be equal to
e to the power k tau.
exponential k tau.
K tau.
You know the value of tau? Am I right? So you can calculate the value of k, isn't it?
Yes, sir.
Yeah. So here you can simply calculate. So in this, again, you will get a straight line. If it is a first order reaction, if I plot PT versus PT plus tau, you should get a straight line, which slope will be given by exponential k tau. And from that, you can calculate the value of k because you know what is the value of tau. You have already fixed that, okay, tau is suppose 30 minutes, then you can simply put 30 minutes here. So these are the two very good methods to calculate the rate of reaction or know order of reaction if if it is not possible to measure physical property at the completion of the reaction. At the completion of reaction. Okay. I will again discuss fast method, very fast method, but not right now. And I will discuss the reversible reaction, then I will discuss fast reaction. So some reactions are complete in 1 minute. How I am going to measure it? Because 1 minute में तो आपका you cannot take the measurement, am I right? There should be manually. It is not simply possible that to measure measure concentration of a particular reactant or a physical property at a given time, or physical property at a given time, even total physical property at a given time if the reaction is fast, because you have some dead time when you are trying to measure a physical property through manual method, right? So for example, between two, at least you need 10 minutes to measure. Even if you are very fast enough, between two measurement, you have to, there will be some dead time, which is like at least 2 minutes, right? But now reaction is complete in 1 minute. Then either you can measure Y0 or Y infinity, nothing more. Am I right? Some reaction are even complete in seconds. What I can do. So those things I'm going to discuss when I will discuss reversible reaction, because reversible reactions are very fast. And so during that time only I will discuss fast reactions. Okay. The next topic which comes is to understand. Now I know that how to get rate law. Am I right? We have already discussed how to calculate the order of reaction. When I know order of reaction, I know rate law. But why I'm trying to get rate law? Because rate law gives idea about the mechanism of the reaction, right? And that is one of the most important uses of chemical kinetics. Once I know mechanism, you already know that if some reaction goes by SN1, SN2, a different set of conditions are required to get maximum yield, right? And so mechanism is very important. And rate law is one of the very important steps to get the mechanism of the reaction. Mechanism of the reaction. So most important application of kinetics is to establish mechanism of the reaction. Okay. So any reaction, if you consider, generally it doesn't go through one step. It consists of more than one elementary steps. Okay. And molecularity, I have already defined that for elementary step, I can define molecularity. That molecularity is basically number of molecules that come together to react in one elementary step. So in elementary step, molecularity is equal to order of reaction. Why order of reaction is not equal to molecularity? But because order of reaction is generally defined for overall reaction, and overall reaction can consist of different rate, different elementary steps, and molecularity of those elementary steps may be different. And so in the next few lectures, I'm going to discuss what are the different elementary steps which makes a reaction. And can we get information about those elementary steps from the rate law? And that is one of the most important application of kinetics. Okay. So yeah, so I will not go ahead. Only thing, let me tell just one more thing, that overall order of reaction corresponds to a stoichiometric equation. Then the reaction probably involves one elementary step. Probably involves. It is not always true. Okay, but if order of reaction is equal to molecularity, it means probably that reaction may have one step, which is not always true. But if it doesn't match to molecularity, it means that, or stoichiometry, I will say, because molecularity is always defined for an elementary reaction. So stoichiometry, if it doesn't match with that, then certainly a reaction involves more than one elementary reaction or one elementary step. So where order is not equal to a stoichiometry, it means it doesn't consist of, the reaction doesn't consist of one elementary step. It must have more than one step. Equal hoga, so there is a chances that reaction can involve only one elementary step, but that is also not sure. So please keep that thing in mind. So I will stop here. If you have any questions, just let me know.
Sir, can you please go to the previous slide once?
Okay. Yes.
Thank you, sir. I just wanted to see something.
Okay. Any other questions?
सर ये अपने लास्ट में क्या बोला था, इक्वल होगा तो भी?
What I am saying, that if a stoichiometry is equal to order of reaction, then the reaction can have only one step, but that is also not true. Okay, कोई जरूरी नहीं है कि होगा. But in that case, there is a chance of a reaction consisting of only one step. Only thing I am saying, this may not be always true. You can look at when we discuss the mechanism, then you can yourself see that it is not always true. But this is always true, that if reaction order is not equal to stoichiometry, then certainly reaction have more than one elementary step. Okay?
Yes.
Any other questions? किसी को नहीं क्वेश्चन है? Please feel free to ask questions. Now things will become more difficult and difficult. So if you don't stop, then you are not going to understand.
Sir?
Yes, somebody is asking?
Yes, sir. Actually, this what this particular slide is trying to say is not very clear to me. I mean,
Okay. So let me go here. Okay. So suppose a reaction is like this: A plus B. Okay, giving you product. Okay, if order is equal to A plus B, where this is reactant A and reactant B, this is stoichiometry for A. Reactant A, this is a stoichiometry of reactant B. So order is equal to A plus B, then this reaction can go through one step only. So it is like A plus BB going to product. There is a possibility.
Okay, just
But if suppose order is not equal to A plus B, then this can happen like this: A goes to intermediate first, then this intermediate can react with BB to give you product. All right? It can have more than two steps also. All right? So what I am saying, in the second case, it is certainly more than one step.
okay.
In first case,
Not
it
necessary.
is it can be one step, it can be more than one step. So that's what I mean by steps. This is a step 1 and this is a step 2.
Right.
Is this okay?
Yes, sir. Thank you.
Yeah. Any other question? No, so I will stop here. So let's discuss tomorrow.